Hey everybody. Today we're going to do a quick little lesson about projectiles and talk about what they are and how we kind of deal with them and why they're maybe so important for us to understand about. All right, so the first thing that you need to do is to take your notebooks, turn to page 33 in the notes. Page 33 says projectile and uniform circular motion guided notes. We're just worried about the projectile part of that at this point. And we're going to get to a few of them today, not nearly all of them, maybe the first 3/4 of that page today. I know there's nowhere to write these definitions that you see over here on the board on your notes, but you're going to need to get them there somewhere. So take just a few minutes, write down these definitions, and we can talk about them as we need to. If you need to pause the video to write these, you can do so now, and I'll resume talking about them when you unpause. All right, so you've written the definitions of these down, of a projectile, of the trajectory, and the range. So let's talk about each one. A projectile. A projectile is any object that's hurled through the air, and by hurled, I mean that can mean a lot of different things, but we mean thrown or fired, like you fire a bullet from a gun, but something like that. An object that's hurled through the air in which the only thing affecting its motion is gravity. Okay, so what can be an example of a projectile? This tennis ball is an example of a projectile. Now, as the definition it reads right now, as I'm holding it, this tennis ball is not a projectile. And it's not a projectile because my hand is influencing the motion of this tennis ball. It's causing the tennis ball not to fall. So my hand is something other than gravity. The only thing that can affect the motion of this tennis ball for it to be a projectile is gravity. So therefore, if I let go and drop the tennis ball, then it becomes a projectile just so long as it's in the air. I can throw the tennis ball up. It becomes a projectile so long as the thing's in the air. Or I can throw it from side to side. And you can see, if I could catch, as you can see, the path of the projectile makes a shape, and you wrote down that shape's a parabola, but that is true. You can actually see it on the screen. Okay, but this is a projectile. Other things that are projectiles are bullets, sometimes rockets, as long as the rocket engine isn't firing, because remember, if the rocket engine is firing and causing accelerations on that rocket, that's something other than gravity that has an effect on its motion. But bullets don't have a rocket attached to them. So bullets, and then we'll see later on that satellites are actually projectiles. We'll talk about that in a minute. So I said this a minute ago, the trajectory is the name for the path of the projectile. And you can see that it is a parabola. And then another word that we're going to talk about when we talk about all this is range. And range, we just talk about the horizontal distance, how far it went left and right or right and left. And a lot of times we'll call this the horizontal distance, but another way to say that is the range. And that's an important term that we need to think about. A driving range or a shooting range is you hit a golf ball down the range, or you fire a gun down the range. And that's what we're talking about there. Okay. The next thing that we need to discuss is a scenario that I'm going to just kind of make up on the board, and that has to do with a magic gun. So I'm going to take this magic gun, and it's magic because I'm able to fire off a projectile, some sort of bullet, at whatever speed that I want to fire it off. So here's the ground, and this level ground, and that magic gun is some height above the ground. So we'll call that height h. So if I fire the gun or the projectile and I select the velocity coming out of that gun is very, very small, almost zero. In fact, let's make it zero. How is this going to behave? And of course, I hope you said that it's going to fall straight down like that. And that's a problem that we've done before. We've taken an object, we've dropped it, we've let it fall straight down, so we can do all the math and stuff for an object like this. But what if I give it a very small velocity, a small firing in that direction? So it may start off this way, but it's not very fast, so it doesn't go very far, and it kind of does something like that. But now we've got a little bit of distance right here that is traveled. Same way if I fire it a little bit faster. It gets to there. A little bit faster, it gets to there. A little bit faster, it gets to there. A little bit faster than that, it gets to there. And I can keep on going like this till the cows come home. And notice that each dashed line that I've made looks like half of a parabola. It's because the trajectories are parabolic. So my question is there any speed that I can select my magic gun to fire this projectile that we can get a line that looks straight and never drops? And hopefully the answer to that is something that you've already said in your head. You cannot. Okay, we cannot fire a gun fast enough that it never drops back to the earth if we have a flat piece of ground. And intuitively, you should kind of understand that because the earth always pulls on the object. It can't be traveling fast enough that the earth said, you're going too fast. I'm just not going to pull on you anymore. The earth doesn't make those kind of decisions, and it always pulls on the object down the same way. Okay, so we cannot ever have anything that looks like this. That is impossible. Now we can fire the gun really, really fast and end up way out here, but it can never be a straight line. Okay. Now, here's a big question. This is like one of the most important questions that you'll end up answering today. Suppose that we take only two of these projectiles. We take one that was fired really fast and one that was not fired at all, only dropped. And we did this at the exact same time. So where we have one bullet that drops straight down like that, and one bullet that is fired straight out, but it ends up making its way back down to the earth. And we do that at the exact same time. We fire it, we drop it from the exact same height at the exact same time. My question is, which bullet hits the ground first? Is it the red bullet that was dropped straight down, or the green bullet that was fired out? So think on that question for just a second. Which one hits the ground first? Now, you might be quick to say it's this one, the red one, because it doesn't have that far to go. But in actuality, that's not what happens. So what I want you to do now is go ahead and pause the video. There is a Mythbusters video attached where they did exactly this experiment. They fired a bullet, they dropped a bullet at the same time. They had really high speed cameras and sensitive equipment to measure the difference in time of when these two bullets hit. And they measured that. And go ahead and pause the video, watch the Mythbusters link, and come back to me. So now that you've watched Mythbusters, you probably should know now that these bullets, in fact, hit at the same time. Now, Mythbusters got a time difference of about, I can't remember what they said, 39.6 milliseconds, I believe is what they said. 39.6 milliseconds is a really, really small amount of time. In fact, it is equivalent to 0.00396 seconds, rounded off to 0.004. I'm sorry, not 0.0396 seconds, which is about 0.04 seconds. To put that in some sort of perspective, to blink your eye, it takes this many seconds. 0.2 of a second to blink and open. So we are way, way faster, or way much shorter time has expired between these two bullets hitting the ground than it is to even blink your eye, which tells us that this number right here, this number that they got, the time difference is practically zero. So if there's no time difference at all, that means they hit at the same time. So why is that? Why doesn't this shorter route mean less time? Well, it's because gravity always pulls things down the exact same way, no matter what they're doing. So an object can be traveling really, really fast this way. It's still being pulled down the same way that an object that's sitting still is being pulled down. That's why we get this kind of look, no matter how fast it's going. It's the same here as it is here and here and here and here and here and everywhere in between. Okay, so let's go back to the magic gun. I had to go get my marker. This time, I'm going to put the magic gun on a tower. So here's my tower. Here's this gun that I can select my speed for my projectile. And we're going to have ground that goes all the way over here. And I'm going to kind of draw the exact same things that I drew before. A very small speed. It hits the ground there. All the way to like really, really fast. Something like that. And we have agreed that nowhere ever is it going to be fast enough to be completely straight. So the one problem that we have with this is kind of the way it's drawn. If the distance between here and here is kind of a small distance, so it's like 300 feet or something like that. If that's 300 feet, then this is a perfectly okay drawing. This is exactly what happens. But if we change this to 300 miles, it might be fairly accurate. But if we change it to 3,000 miles or even 30,000 miles, then this is not an accurate depiction of what's going to happen. And why not? At 30,000 miles and even 3,000 miles, the Earth is not flat. The Earth's a globe. So I don't have flat ground like this to infinity, to 30,000 miles. I have now curved down. So the curvature of the Earth, and I know this is not a very good scale, but we're kind of exaggerating everything right now. The curvature of the Earth makes it a sphere. I don't know how good of a circle I'm drawing right now. It's probably not very good. That's all right. And there's the center of the Earth. So as long as I have fairly short distances, which, we think of, firing a gun or throwing a ball or something like that to be fairly short distances, they're, real tiny on the globe. Like the width of Georgia is about right at the width of the black part of the tip of the marker. So very small scales this happens on. But when you zoom out, the first one, real slow, hits right there, and that's fine. The second one doesn't hit right there. It hits all the way down here. So it travels a little bit longer distance. This one travels an even longer distance to get there. This one travels, if we continue the parabolic curve, this one travels right here, so it hits over here. So it's almost like you were standing at the North Pole and you fired your gun south, and it hits down here somewhere around the United States because the Earth drops off. Okay? But what happens if you fire this gun? If we continue this parabola, I've missed the Earth completely. But remember, the Earth, when the object gets right here, the Earth is still trying to pull it towards it. Even when I get to right here, the Earth is still trying to pull it towards it. So it continues in this path around the Earth that we call orbit. So you might have seen a launch of a rocket, or maybe old footage of the space shuttle, which we no longer use anymore. And you might have seen the rocket go up and then start to pitch this way. That's because in order for us to get into orbit, it's got to have some sort of really, really fast speed that way with respect to the ground. Okay? In order to get into orbit. Otherwise, it's just going to go straight up and come straight back down. Okay, what goes up must come down. That's true. Unless it goes up and then it goes really fast sideways. So fast that every time it falls, it just misses the Earth every time. And this is what we call orbit. There is no line above the Earth somewhere that we call space. We can't just build a big ladder, climb that ladder, and when we get to some random point, we say, hey, we're in space. And then we go back down one more rung and say, now we're not in space anymore. We can't be in space, not in space, be in space, not in space. Okay. What happens is the air molecules of our atmosphere slowly fade out. So it's not just, I'm in the atmosphere, I'm in the atmosphere, I'm in the atmosphere, I'm in the atmosphere. I'm not in the atmosphere anymore. So just because you get above a certain level or a certain height above the earth doesn't mean that you're floating in space, okay? It might mean that you've run out of breathable air, but it doesn't mean that you're floating because gravity still exists. The only reason that you float in space when you're in orbit is because you're falling. So think about a roller coaster. When you go up the big hill of a roller coaster and then you start way down, think about how you feel. You lose your stomach. Same way like on a car, if you're driving real fast on a hill. Think about having that sensation all the time, as long as you're in orbit, because that's what the astronauts are doing. They're falling. They're just missing the ground every time they fall. And how they train astronauts to do this, which is a really cool thing to do, they have a modified like passenger jet, and they are able to take all the seats out of that passenger jet and put padding in kind of a big area, big cargo area, and they'll fly the jet, and then all of a sudden they'll tell the astronauts, the ones that are training, all right, y'all get ready, and the pilot will just go into a nosedive. And as he goes into a nosedive, that's basically in free fall, and so you're now floating around, and you get to do that for, I don't know, 2 or 3 minutes or so until you start to get closer to the earth, where the pilot has to come out of that dive, and then he climbs way back up to high altitude, and he does it all over again. In the airplane, they've kind of nicknamed the vomit comet because, you can probably understand why. But that's how the projectiles work. And that's why I said that satellites were projectiles, because satellites are in orbit around the Earth. And they have to get to a certain velocity in order to get into orbit. Now, once they're in orbit, they don't have to fire any kind of rockets or anything like that, because there's so little air molecules, so few air molecules in what we consider space, that once it's got some sort of speed, it can just keep that speed and doesn't have to correct it. Okay, and we'll talk more about that when we talk about Newton's first law, that objects in motion stay in motion and objects at rest stay in rest until acted upon by an outside force. There's very little outside force to influence that. And because the only thing practically that's influencing the motion of the satellite is gravity, because it keeps it in a circle, then we consider that a satellite is a projectile. Okay, so looking at back on page 33 of your notes, I'm not going to write these down on the board. I'm just going to read them to you. So make sure you follow along just to kind of get the gist of what we've said today. All right, so it talks about on the top of page 33, it mentions the Mythbusters fired bullet versus drop bullet. So that's the video you watched. If you want to watch it again, feel free. But we're going to make some conclusions about that video. The conclusions are that horizontal motion is independent of vertical motion. It's independent of vertical motion. So what does independent mean? It means that it does its own thing. If you're independent from your parents, that means that you don't have to rely on your parents to do anything. Your parents don't rely on you to do anything. You are a separate thing. So horizontal motion is a separate thing from vertical motion. Anything can be happening horizontally, meaning left and right, but that does not affect anything that's going on vertically, which is up and down. We will also see that vertical motion is independent of horizontal motion. Same way. Because one is independent of the other, that means the other is independent of the one. Okay, so both of those blanks are independent of. This means that we can solve projectile motion problems by dealing with horizontal and vertical motion separately. Okay, and this is going to be really, really important when we start to do these problems. We already know how to do these problems. You've already done problems where a ball has been dropped. You've already done problems where a ball rolls along a track, a straight track. So a straight track is the horizontal part, a ball drop is the vertical part. Those two things we've already done. Now we just got to kind of piece them together. I used my magic gun example. They use a ball rolling off a table example. It's the same thing. When a ball rolls off the table, it's an excellent example of a projectile with the horizontal initial velocity at the time the ball is launched off the table. The ball becomes airborne when it leaves the table. If the ball rolls along the table with constant horizontal velocity, then at the exact moment that it leaves the table, it's going to have the same horizontal constant velocity that it rolled off the table with. Basically, what that means is this. If you have a ball that's rolling at 50 miles per hour, I know that's kind of weird, but let's just say it like that. If it's 50 miles per hour here and it's 50 miles per hour here, then once it becomes a projectile and it has a parabolic path, then if you were to measure the velocity at any point along this line in this direction, you would get 50 miles per hour. 50 miles per hour. 50 miles per hour. Right up until the point where it hits the ground. Okay? Because it does not accelerate in that direction. Gravity does not pull sideways. Gravity only pulls down. In the horizontal direction, there are no forces on the motion, which means no acceleration. It's kind of what I just said. So we're looking at the sentence that's right under the picture. In the horizontal direction, there are no forces on the motion, and that means there's no acceleration. Horizontal velocity remains constant. The ball continues to travel horizontally through the air at the exact same speed that it was rolling on the table. 50 miles per hour, 50 miles per hour, 50, 50, 50, and everywhere. This is not true in the vertical direction. In the vertical direction, there is acceleration. The projectile accelerates downward at negative 9.8 meters per second squared, according to gravity. Just like it would do if we dropped it. Remember, motion in this direction is independent of motion in this direction. So whatever we're doing here doesn't matter. So we could be going 50 miles an hour, we could be going 1 billion miles per hour, we can be going 0 miles per hour, and you treat this as the same. When you combine the two motions, the trajectory, the path that it takes, is going to be a parabola, or in this case, half a parabola, but it's still a parabolic path. So where are we going with this? What's the point? Why are we doing this? Well, let's suppose that you are some sort of investigator and a car was driving off a cliff. Maybe it's by accident. That car had some velocity, some speed as it was driving off the cliff. And that cliff is so high, call it a height of H. And as soon as it leaves the cliff, it falls in a parabolic path into some crash. And that crash is some distance d away, which would be the range. So we're going to be able to solve for all of these things. We're going to be able to tell how fast the car was going as it travels off the cliff, how high the cliff was, how far over it went, and we're also going to get to look at how much time did the object spend in the air. In his case, maybe to say a prayer. Or in the case of our labs, a ball rolling off a table, and instead of a crash, where the cup goes to catch the ball rolling off the table, which is a real lab that you guys are going to do next week. So this is where we're going with all this stuff. Hopefully you understand about trajectories, projectiles a little bit better now. And the main few things that we learned in here were these. Number one is if you drop a bullet from the same height that you fired a bullet horizontally, no matter how fast you fired it horizontally, those two bullets are going to hit at the same time. That's number one, most important. Number two, most important, is there is absolutely no velocity, no speed fast enough that we can fire a gun or throw a ball horizontally that it will never be affected by gravity. Okay, gravity's always going to pull it down. And number three, the third most important thing that I hope you got out of this is that motion in the X direction, this way, and motion in this way have absolutely nothing to do with each other. Anything can be happening in this direction, and it doesn't affect what's happening in this direction. In the same way, vice versa. Anything happening in the Y direction has no bearing on what happens in the X direction. Hope you got those things. Hope you guys have a great day, and we'll see you later.